Assalamualaikum, my name is Muhammad Akwan bin Mamasri and my meeting number is TE180088 and I am from Group 3, would like to present our group assignment. So for the task 1, this is our group flowchart. So our flowchart start with identify the problem and then discuss on empirical modeling and controller designing. So at here, our group has to design the PID controller. So to design the PID controller, need to do a mathematical calculation to get the transfer function. So to get the transfer function, our group have decided to use a FOPDT method, which is first order plus that time method to get the transfer function. And then to find the PID parameter, which is KP, KI, and KD, our group has decided to use a Ziegler-Nichols tuning method to find the PID parameter. And then we can design the PID controller in a simulation on a MATLAB. So if the result from the PID controller do not meet the requirement, we need to add anti-wind dart at our PID controller. And then if the result have meet the requirement, and we can proceed to do the analysis and end of our assignment.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azizan Kadir. Number metric DE190120, and I will be presenting for the manual calculation part for this assignment. So what we can see here is the open loop response graph. So the first thing that we need to do is we need to find the x-axis and y-axis scale. So the range that I get is 1.6 centimeter is equal to the 100 second. So the 1 millimeter is equal to 62.5 second. For the y-axis, the range that I get is 1 centimeter is equal to 10 degrees Celsius. So the 1 millimeter is equal to 1 degree Celsius. Okay, next, we need to find the deeper slope. So here is the line that I draw, and then from the minimum, which is the initial starting, I will draw the line so it will cross the deeper slope to find the theta, which is the time delay. The theta is 250 seconds, and then we need to find the value of the A, which is the S and the M. So the value for the A is 72 degrees Celsius. After that, we need to find the 63.2% output response from the graph. So using this formula, the value that I get is 73.5 degrees Celsius. So from the graph, I will draw the line until it clashes with the slope, and then I draw it until below. So then we can find the tau value, which is the time constant. So the tau that I get is 3,750 seconds from this line until this line. So then after that, we need to find the process gain, which is the K. So the value of the B, I get it from the input CL, which is the 20 milliampere, and then the final value for the K is 3,600. So after we get all these three value, we can input it into the FOPDT model, which is this one. So here is the final value for the FOPDT model. So after that, after we find the FOPDT model, we need to find the PID parameter. So the PID parameter that my team using is Ziegler-Nichols tuning formula, which is to find the KP, TI, TD, KI, and the KD. Okay, for the KP value is 0.005 and the TI value is 500. The TD value is 125. The KI value is 0.00001 and the KD value is the 0.625. So after we find all the PID parameter, now we can find the PID, which is the robust PID parameter. So the robust PID parameter is tracking time constant, which is the TA. The TA value using this formula, which is the 250. And then we need also, we need to find the 1 over TA, which is the final value is 0.004. So after we get all the value, now we need to test it on the task given. So that's all from me. I will pass to the next presenter for presenting the task 1. Thank you.
Assalamualaikum and good afternoon. My name is Muhammad Arif bin Mahir and my metric number is DE1800075. So then I would like to continue with the PID controller, which is for the task 2, and we decide on using a Ziegler-Nichols method. So this is our PID design using MATLAB. So firstly, I will open the MATLAB. So this is our PID design. So first, for the block step, so we decide 75 as the final value. Next, this is the 3 gain, which is for the PID controller, which is proportional gain, integral gain, and derivative gain. So this gain obtained from Ziegler-Nichols formula. And next, at the saturation has been set 20 milliampere due to the input given. So this is the transfer function that get from the FOPDT model. Next, this 28 set here, set as a initial temperature for the constant value. And lastly, for the scope, to get the output response for the PID controller. So first we need to click run. Okay, after that. So this is the response that we get. And from here, we can get the time domain analysis, including rise time, peak time, settling time, and overshoot percentage. So back to the slide. So this is the manual calculation for the determination PID parameter using Ziegler-Nichols tuning formula. So for the proportional gain, this is the result, which is 0.005, and for the integral gain, we get 0.0001 over second, and lastly, derivative gain, we get 0.625 second. So next, this is output response for the rise time, if we can see from the graph. So basically, for the formula for the rise time, which is 90% times by set point, which is our set point 75, and 10% times by 75, which is the set point, and we get the final answer. So for the peak time, we can see at the peak, and that is our result for the peak time. Next, for the settling time. So based on the graph, this is our settling time. Basically, settling time based on a graph that move based on the upper and lower band. So basically, for the formula, here I set as 2%, which is 2% times by 75, and then we get the answer. We need to plus for the upper band and minus for the lower band. So lastly, this is our time domain analysis. Based on the table, we can see this is the result for the rise time, peak time, settling time, and lastly, percentage overshoot. For the percentage overshoot, the formula basically Cmax minus by set point, divide by set point, and times by 100, and then we get the final answer. So that's all from me for the task 2. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Aiman Ali Zainal. Now we proceed the presentation on the robust PID design. So in our robust PID design task 3, we use back calculation and tune up. to solve the problem in the normal PID to ensure the parameters or the response follow the desired specification given by merah chemical holding. So in our anti-mirap calculation, they involve 3 additional component, which are 2 summing junction and 1 additional gain. So the gain here is calculated using formula TA equal to square root T integral multiplied with T derivative. So we got TA equal to 250. So our final gain is equal to 1 over TA, which is 0.004. So we proceed on the PID, robust PID design. So for our robust PID result, so you can see here is the response for our PID. And then to find the percentage of our overshoot is we use this formula, maximum overshoot minus with set point over set point multiplied with 100%. So we got 1.24%. And then for the setting time, so the setting time is taken between the initial response to the plus minus 2% from the set point. So in our case, the range of the band are between 74.06 degrees Celsius to 75.94 degrees Celsius. So our response reached the setting time at 4072 seconds. The rise time is taken from 10% of the response to 90% of the response. So in our response, the 10% of the response is at 32.7 degrees Celsius, while 9% of the response is at 70.3 degrees Celsius. So the rise time of our response is 3067 seconds. So for the steady state error, there is no steady state error in our response, which is the response are approximately at 75 degrees Celsius. And then for the comparison of the desired specification and process variable, so we're able to get overshoot below than 3%, which is at 1.24%, and setting time we're able to get lower than 4250 seconds, which is we got 4072 seconds, and the rise time we got 3067 seconds, which is below than 3300 seconds. And the last one, for the steady state error, we have 0 steady state error.
So in a conclusion, by following all the steps discussed with all team members, able to develop a controller for the heating process. So the first order plus that time, which is FOPDT, has been used to find the transfer function for designing the PID controller. Meanwhile, the Ziegler-Nichols tuning formula was also used to gain the PID parameter. So with the value of Kp, Ki and Kd, the PID controller has successfully been designed. But the result obtained does not meet the requirement given by the merah chemical holding. So therefore, to improve the transient response of the PID controller, the PID controller need to adding anti-wind-up. So as a result, the overshoot of the response is 1.24%, which is below than 3%. The settling time is 4072 seconds, which is below than 4250 seconds. So the rise time is less than 3300 seconds, which is at the 3067 seconds. And last but not least is there is no steady state error for this response. So therefore the process variable had fulfilled all the desired specification given by the merah chemical holding. So that's all from our group. Thank you.